Welcome to the 20th lecture in Physics 10 in 30 lectures. We are completing our coverage of electromagnetism this week, and we start with this lecture on magnetostatics. We will start with an overview of chapter 10. It is another long chapter, and we will split the topics in chapter 10 across two lecture sets, this and the next one. After the chapter overview, we cover the introductory materials in magnetism, such as permanent magnets you have no doubt seen and played with. We introduce the field idea in the context of magnetism and look at the illustration of magnetic forces on a current carrying wire. Then we go over right-hand rules in lieu of a fuller coverage of cross product. Right-hand rule gives the direction of the vector that results from cross product. We have additional demonstrations of magnetic forces, this time on an electron beam, and we wrap up this lecture by developing some intuition for magnetic field directions with additional right-hand rules, and a discussion on magnetic units. In the next lecture set, we will talk about electromagnetic induction, still part of chapter 10, and useful modern devices such as motors and generators. Now, we start with chapter 10 overview. This is overview video for chapter 10, magnetism. This is another long chapter like the chapter for electricity, covers a lot of topics, a lot of quite mathematical topics, so the level at which we can cover in this conceptual physics will be necessarily limited, and I will highlight some of those areas in this overview. By the way, this introduction, I think for whatever reason, Notebook LM got confused a little bit and created this node for I guess a section 10.1 introduction to magnetism, but the first section is always kind of overall intro to the chapter. So I mean, you can read about this in section 10.1, but I don't think I ask you any homework questions on those. The real content starts with section 10.2, magnet, where we cover the material that I hope a lot of you find familiar, being a person having lived in modern age, with a lot of modern devices, fridge magnets, bar magnets that you may have seen earlier. And a lot of these features are, I think, both of the features that you would have seen with the household items that you might have played with, and also with the analogy to electricity. So north and south poles in a lot of ways act like a positive and negative charge. And like poles repel the same way like charges repelled, and unlike or opposite poles attract the same way unlike or opposite charges attracted. Now, what sets magnetism apart from electricity is that there are no such things as magnetic charges, or what we would have called a monopole. You couldn't have North Pole by itself or South Pole by itself. You cannot have a kind of net number of poles, kind of an excess of North Pole over South Pole. Whenever you have North Pole, you will always have the same amount of South Pole. They always come in pairs. So if you imagine a bar magnet and you break off the bar magnet, each broken piece becomes its own complete bar magnet with the north and south pole. And you might have seen compasses, they work because Earth produces its own magnetic field that can be modeled like a bar magnet. So that's section 10.2. In section 10.3, ferromagnets and electromagnets, you will see some discussion of ferromagnets as again kind of drawing on your experience of things that stick to magnets. Some of your cookware would stick to magnets. Magnetic domain is a way of explaining how ferromagnets are different from other types of materials. And I don't think we get into Curie temperature in the lectures. This is a kind of a transition temperature, below which you can have ferromagnets and above which you don't have ferromagnets. For a lot of ferromagnetic materials, this is actually a pretty high temperature, like close to the melting temperature of the iron. And electromagnets, I guess I would say it hints a little bit at the content you will see soon about more of the fundamental nature of magnetism. For the purpose of the section 10.3, electromagnets are temporary, being powered through electric current, and this is where you would care about the magnetic properties of materials. You can produce a larger magnetic field with the same amount of current if it has ferromagnetic core. And superconducting magnets, I don't think I talk about that in the lecture at all, except maybe in talking about magnetic units. So the largest amount of magnetic field we can produce with a superconducting magnet is around like 50 Tesla, less than 100 Tesla on a continuous basis. So that's section 10.3, magnetic materials or ferromagnets and electromagnets. Now, we start our coverage of magnetism in a more fundamental way, starting with the magnetic field. Oftentimes you will see us use the letter B, kind of contrast to letter E for electric field, to indicate magnetic field. B field is magnetic field. So section 10.4 introduces magnetic fields and magnetic field lines, and this is why we spent some time on electric field lines. If you have a good intuition for electric field lines, you can transfer that right over to magnetic field lines. They are quite analogous to each other. So magnetic field lines, just the way electric field lines went from positive to negative charge, they go from North Pole to South Pole. And some of the rules you have seen for electric field lines continue to hold for magnetic field lines. In a drawing of field lines, the strength is indicated by the density of lines. And as we said before in talking about magnets and poles, because there are no magnetic monopoles, no magnetic charge, unlike electric field lines, which could start on a positive charge and end on a negative charge, magnetic field lines don't really start on a North Pole and end on South Pole. I mean, you can draw it that way, but as you are drawing it that way, it ends up forming continuous closed loops because there are no isolated North Pole or isolated South Poles that can serve as an origin and sinks for magnetic field lines. But other than that difference, so if you are drawing electric field lines for a net charge 0 electric charge configuration, it would look kind of similar to an analogous version of magnetic field lines. So as you are developing your intuition for magnetic field lines, I want you to lean on that analogy to electric field lines. And in a few sections, we are going to look at the effect of those magnetic fields. The first of the effects of magnetic fields we will look at are the fundamental interactions involving magnetic fields. That is, the most elementary interaction involving magnetism, which is actually not between two poles of a permanent magnet. Those are actually quite complicated interaction involving quantum mechanics. So the most elementary interaction is the magnetic force exerted on electric objects, on electric charges and electric current. So we describe the magnetic force on moving electric charge. This is the context in which we introduce the right-hand rules. And we do this in place of properly introducing what's called the cross product. It's a kind of a vector product that you will see introduced in Physics 4A or Physics 4B if you take those classes. In this conceptual class, I think that's too much math. So we will fall short of actually introducing the cross product, although some of the mentions will refer to it kind of obliquely. We will instead talk about the right-hand rule. So in the textbook, we introduce the right-hand rule in the context of magnetic force. We do give you a formula for magnetic force, the kind of the maximum magnetic force that can be on a charge, Q, electric charge, moving at speed v in a magnetic field of strength B is given by this product, Q times V times B. And it says maximum at 90 degrees because the magnitude of this force depends on the relative direction of the velocity and magnetic field. If the velocity and magnetic field are at 90 degrees, that's where you get the maximum magnitude of the force. If there is some angle, then the force is reduced by the factor of sine theta, where theta is the angle between these two vectors. Now, force is a vector, and for the direction of that force vector is where we introduce the right-hand rule. The lectures will cover it, so I'll leave that for the lecture. The lecture uses the directions of the vectors v and b and how that's related to the vector f. Oh, and the unit, there is a separate unit talking about the magnetic field unit. Look at the lecture. Tesla is the basic SI unit of magnetic field, but Gauss is also quite popular among experimentalists who work a lot with the magnetic field. Now, this gives the amount of the magnetic force on a moving charge, like in an electron beam, and I do have a demo for that. But the more common examples of magnetic forces you will see is on current carrying wire. So for magnetic force on a current carrying wire, we have a slightly different form of the magnetic force. This can be related to the magnetic force on a moving charge. Oh wow, with this font it's really hard to see. It's saying magnetic force F is equal to I, the amount of current, times L, the length of the current carrying wire, times B, magnetic field. So ILB. The capital I and lowercase l are really hard to tell apart. And this again is at a maximum at 90 degrees, where the direction of the wire and the direction of the magnetic field are perpendicular to each other. That's when you would get maximum force. And in one of the later lectures, you will see me analyze an electric motor. The expressions I use for that comes from this basic relationship for the magnetic force on a current carrying wire. All right, so these are what's covered in sections 10.5 and 10.6. And 10.7, motors and meters, talks about electric motors and kind of meters based on the magnetic force. But I don't think this notebook LM mind map includes that. It's kind of a small section, so I think it got left out. In terms of lectures, you will see motors covered later, after we have introduced electromagnetic induction. So you will see it in the second set of lecture videos. Section 10.8, magnetic fields produced by currents, Ampere's law, is covered here in this note, current created fields, Ampere's law. Now, if you look at the textbook section, you will see, rather than the statement of Ampere's law, more of an excuse for why we can't state it. Even to say the Ampere's law, we need the calculus. So I can't quite give you Ampere's law without going beyond the mathematical material that I'm allowed to use. But in a later lecture, when we are starting to introduce light, I will actually list the Maxwell's laws of electromagnetism and just to give you conceptual summary of those laws. Now, in this section, we introduced what your textbook calls right-hand rule number 2. this relates the direction of magnetic fields to the current that's producing the magnetic field. And in a separate lecture, I cover another shortcut rule alongside this shortcut rule. This shortcut rule gives you the direction of magnetic field due to a long, straight current carrying wire. And there's two more geometries, and I will lecture separately on these to illustrate the kind of magnetic fields produced by a circular loop of current and a solenoid current. So this wraps up the material that I will cover in the first set of lectures about magnetism. Again, this is a long chapter, so to do each set of topic justice, I have to break up the lecture into two. This week you will actually see 3 sets of lecture videos because we are also covering light this week. The remainder of the materials, what relates to section 10.7 and 10.9 and 10.10, and I don't think I actually cover 10.11 and 10.12 in separate lectures, but the materials relating to these later sections, you will see that in a separate lecture video. And let me just go over them so I don't have to do part 2 of this overview video. So this was section 10.8. So in section 10.9, induced voltage and magnetic flux, we introduced the fourth and the last of the Maxwell's equations, or at least we allude to it. So the electromagnetic induction is what you might call Faraday's law of electromagnetic induction. And I think I actually give you the statement of Faraday's law. Faraday's law relates rate of change of something called magnetic flux, which is basically magnetic field times area, to the induced voltage. And in a separate lecture, I'll give you more conceptual motivation for Faraday's law. Now, Faraday's law is also complex enough that there's a part in it that has a minus sign that we give it its own name. We give the name to that one minus sign of Faraday's law. We call that Lenz's law. I guess, you could summarize it as opposition to change, or it's kind of a mouthful. Let me try to state it. So when you have Faraday's law acting around the conductor, there's a conducting path, then the induced voltage will induce current within that conducting path, and the direction of that induced current is such that the magnetic field due to the induced current will oppose the change in the magnetic flux that originally induced that voltage. Again, it's a bit of a mouthful. I'll cover this in a separate lecture. But Faraday's law is super important. This is basically how electric generators work. Any power grid, kind of the modern infrastructure of electrical power, most of it comes from electric generators. So, excepting, let's say, solar energy, most of it comes from electric generators. And the principle on which electric generators work is Faraday's law. And I have a demo that illustrates how electric generators and motors are related to each other. And sort of relating to that power grid, electric generators, is what sections 10.11 and 10.12 covers, applications and power. And I don't think I covered this in any of the lectures, transformers and AC versus DC. I'd say read through that in the textbook just to get some sense of what's covered in the textbook. But no pressure, because I don't think any of these are covered in the homework questions and not in any of the lectures. So just read through sections 10.11 and 10.12, and whatever you feel you understood, that's great. Whatever you feel you didn't understand, no pressure. There's nothing, no homework question that I'm asking that you have to answer. So that covers all the topics in chapter 10. Again, it's a long chapter. It covers almost like 1.5-2 lecture sets worth of material. So you will see materials relating through the current created fields in this first lecture set, and the remainder of the materials you will see in a separate lecture set. Thank you. Bye. Welcome back. So we are starting with the new topics today with magnetism. And magnetism is a little bit weird. In some sense, you guys have more familiarity with the magnet. As in, most of you kind of remember playing with the fridge magnet, and it doesn't, it doesn't surprise you that to start off with, how many people know what this is? What does it look like? It kind of looks like propeller. It's compass, as in, right? And it doesn't surprise anyone when I push it a little bit and let go, that it kind of comes back to where it was, right? Can someone say what compass is for?
It allows you to know the direction of the poles up on the Earth.
Yeah.
It allows you to travel
Direction of poles. So people use for navigation for thousands of years. Anybody here know which direction is north in this room by chance?
No.
That way? Okay, so this must be the North Pole. And
No, north is that.
what?
Because that's the Bay Area. The Bay is here. So there's
Let's see. I'm trying to imagine the map. So Science Annex is here. The campus is to the west of Science Annex, right? So north. Okay, so the blue end must be north. And it doesn't surprise anyone that when you see this thing suddenly moving around, you don't think I'm, performing magic tricks or anything. Magnetism, in some sense, you are already familiar with it. And when I take this bar magnet, which already has north and south label, so we figured the blue end must be north, and it repels from north, attracts to south, or south end repels from south. All of this seems familiar to you, right? So I say magnetism is weird because, so let me, by the way, pass this around. I'm going to pass one more thing around, but figured, why do I get to, sorry, I don't know what else you would do with it here. Let me send around another magnet with it. Here's the neodymium magnet to go with it, so that you have something to do with it. I don't know. So, in some sense, you're already familiar with all this stuff already. And this picture is something that illustrates something that many of you have probably seen. So what this overhead camera is showing right now is just, so these are just the array of tiny compasses that you have seen. And when I bring this bar magnet around, what you're able to see is that the bar magnet affects the direction of these tiny compasses as I move it around. And if I put this in the center, does this picture look familiar? Like you have seen before? Yeah, you have many of you have seen this even before we did any electricity, and it kind of resembles the electric dipole field, but as we mentioned when we were doing electric dipole, you have kind of seen this before, right? So yeah, so in this sense, a lot of the introductory material for magnetism, it's something that you have seen before, just by nature of having gone through education in the 20th or 21st century. And none of this is new. And let me just do one last thing. This is one of the demos I found in the closet, and it's kind of a cool demo. I'll pass this one around. This is the cool one that, it's something that you can imagine, but you maybe not have seen. So this illustrates electric or magnetic field in 2 dimensions. It kind of looks like electric field you have seen before. This can be used to illustrate magnetic field in 3 dimensions, because it's a solid 3-dimensional object. I can try to show it to you on the overhead thing, but it's not as impressive there as to seeing it yourself. So first you have to shake it to distribute the iron filing evenly around. Once it's down there, oops. Then what I have to do is before they settle under gravity, I have to kind of put this in the middle. And you can maybe see, I don't know, this is why I thought it would. Can you kind of see the iron filings gathering into the dipole field pattern. And because this is 3D, if you kind of turn it around, then you can see what the magnetic field looks like in three-dimensional shape. So let me pass this around. The way I recommend that you do it is, first to shake it. You have to evenly distribute the iron filing. It'll settle into the, pictures that don't look as good. And then, put in this magnet in here and see sort of the kind of shape that forms. So it's a fun demo. I have it, so might as well make some use out of it. So, all of this you have seen before. Nothing here is all that surprising. So let's start out with some definition of terms that we are going to be using. So we should define them so that I can make sure everyone knows what I'm talking about when I do that. So let me just write down some magnetism terms. So I guess the term I want to start out with is magnetic field. And when I mention magnetic field, if you are thinking of electric field that we have talked about before, it'll be a good place to start. So for now, I don't really want to define magnetic field quite yet. We'll get to it. But for now, for your intuitive feel, I want to say it's similar to electric field, except that it's dealing with a magnet, right? So when you're dealing with a magnet, so this magnetic field, which you can see here, so this is the visualization of a magnetic field, as in you can imagine following these lines and drawing the magnetic field lines the way you have drawn the electric field lines. Right? That's why we spent so much time on electric field, because the intuition you build for electric field will also be relevant when you're dealing with a magnetic field. But field is a bit of an abstract quantity, as in the orientation of these tiny compasses. They illustrate the magnetic field, but these tiny compasses are not magnetic field themselves. It's like with the electric field. Once I place a magnet in space, then just because there's a magnet here, that modifies the space around it to have that magnetic field. Whether you have something in that space, like test charges in electricity, something in space to illustrate the field or not. The field simply exists there, whether you have something to see it with or not. So with the electricity and electric field, we said, electric field interacts with electric charges. And the expression that we fell on many times was, electric force is given by charge times electric field. So what we want to have a word to describe it is, what does magnetic field interact with? Magnetic charge. So let's just start out with just the magnet. If you are talking about, that this magnetic field interacts with magnet. When I talk about magnets, what do you imagine in your head? Like, wait, where's my bar magnet? Oh, okay. The bar magnet that KD is holding, is that more or less what you imagine when I talk about magnets? Right? So when you have a magnet, it has two poles. It has north pole and south pole. So it has these two poles. And I guess there's a reason we call them poles instead of using the same word we used in electricity. In electricity, we would have, so let me draw the analogous version in electricity. When we were dealing with electricity, we had the electric dipole, right? And when we had the electric dipole, we had a positive charge and negative charge at the two ends. And in a dipole configuration, we would talk about how far they are separated. And this whole thing combined as a whole would be an electric dipole. But except when we are, referring to this particular combination, we would call this object electric charge. So the question is, why do we use a different word for this? Why do we simply not say it's a north charge and south charge? Like, in other words, how is magnetism different from electricity in one key way? This is something I hope you already know. I mean, I'm just trying to highlight it. But magnetism is different from electricity in one key way.
One has powerful and the other one does not.
Strength, you mean?
Strength.
They're about equally strong. I mean, okay, it depends on, let me put it this way. Magnetic force can be as strong as electric force. So in terms of the strength of interaction, they're about the same.
So can we say they're a flow of energy in a dipole where they're in a...
Everything has energy. It's something more fundamental, something that you already know. If you play with any kind, where's my compass? Oh, okay, I kind of need that for my next illustration. So you guys have played with the compass and, a magnet that came with it. So you've seen that one end either attracts or repel the other end, right? And what we've seen before was that the blue end was the North Pole. So if I have my magnet here, if I have magnet here, then the North Pole would repel the North Pole of the compass. And all of this is similar to electricity, as in like poles repel like, or South Pole repels south. Wait, is it repelling? Huh. You might have got, okay, South Pole repels south. Some of my compasses are demagnetizing. And the North Pole attracts the South Pole, or vice versa. South Pole attracts the North Pole. Okay? Now, here's something you might have seen as a child playing with a magnet. So this magnet is actually broken. I keep trying to hold it as one piece, but it is broken. When you break the magnet, now, I have a North Pole, and I want to use this North Pole to attract or repel the North Pole there. And when I try that, this is what I get. It actually attracts. What happened? I mean, I'm holding the North Pole, but why is North Pole attracting the North Pole instead of repelling it?
Now it's split again, so now there's another South Pole.
Yeah, this end is still the North Pole, and the bottom is actually now a South Pole. So if I make sure to bring the top end closer, then that'll repel the North Pole. But if I turn it around and bring the other end, this is actually South Pole now. Like everyone knows this, right? I'm not telling you anything you don't already know. Yeah, I won't ask because I'm not trying to embarrass people. But if you didn't know, then you should know that there's something funny going on with the magnets that wasn't with the electric dipole. So with the magnets, if you imagine breaking up into two pieces, then there's north and south within the material. So, I was asking why do we call them poles rather than charges? One of the reasons would be this is how you always see magnet. You never see North Pole by itself. You never see South Pole by itself. If you were ever to, you would actually call that monopole. And magnetic monopole is actually a pretty interesting topic of research. People have been looking for it for a long time. There were a couple signals that people could not reproduce later. Magnetic monopole is something interesting to look at if you're interested, but we're not really going to get into that. For the purpose of this class, every time you see a magnet, it occurs always as a combination of north and south. So this is what we are used to referring to as a magnet is what we would call, to be technically complete and correct, what we would call magnetic dipole. And almost everything about magnetic dipole is similar to the electric dipole. The one difference is that in electric dipole, you could imagine separating that. You could imagine taking positive charge, and that's it. You turn the electric dipole into electric monopole. Like, that's nothing unusual. But with the magnetic dipole, you cannot do that. If you try to separate, this will just become dipole on its own. None of this is surprising, right? So, yeah, so in terms of qualitatively dealing with the magnets, a lot of this is what you, once again, already know. But I started by saying that study of magnetism is a little bit complicated, strange, in the sense that if I'm talking about very qualitative description, it's something that you're already familiar with. In fact, I hope you have better intuition for this stuff than you did with electricity, just from having seen it more. But once we start getting into the fundamental description of magnetism, as in the kind of stuff you really cannot cover in high school physics, maybe you can do, depends on your teacher, can't really cover in high school physics, and definitely not in middle school or before, it gets more complicated. So for electricity, I had this simple expression that I could write down and could always refer to. As in, if you're ever confused about electric field, think about this. You understand force, this is how you get electric field. I will not be able to write down a similar expression for magnetism. So it's not as though I can write down, magnetic force is equal to some magnetic charge times, I'm going to have to introduce a new symbol for magnetic field. We use a symbol B for magnetic field for some reason. I'm not sure why. So it's not as though I can write this down. This is wrong. Any guesses why that would be wrong? Like why I wouldn't even bother trying to guess that expression that magnetic force is equal to, charge times magnetic field? There's no magnetic charge, right? So it's not as though that's really why. Now, if we had magnetic charge, then this would work. But we don't have magnetic charge. So we have to somehow describe force due to magnetic field that's not on a magnetic charge. It's on something else. So, we could talk about force on a, magnet. That's what we are describing here. And that's the experience you are familiar with. But I'll tell you that magnets are complicated. It's so complicated that we are really not going to get into magnetism of material all that much. I should mention these three words so that at least I can say that I have mentioned them. It's not, once again, this is not something we are going to go deeply into, but when we talk about magnetic properties of materials, there are three words used to describe how a particular material, how a particular atom or molecule or particular material responds to magnetic field. We call them diamagnetic stuff. This is what you would expect sort of using classical physics. And I'm guessing it's most common. I don't know, I'm not a material scientist. And there's something called paramagnetism. So there are things that are paramagnetic. And the final thing is something you might have heard before, just because it comes up in everyday life from time to time, something called the ferromagnetic. So this is one of those places where if you are one of those students who do well in spelling bee, then that would help you with these. Versus something no longer being ferromagnetic above the temperature. All of that is actually getting to why that happens. That's opposition material. Describing that those things are there, I'd rather leave that to your reading than spending a lot of class time. So this is maybe the first of the things that says magnetism is somewhat complicated. That even though it's something that you are more familiar with than electricity, it's trying to treat magnetism like the way we treat everything in physics, as fundamental, basic property of nature, it already gets complicated. So what I want to start, or start the proper coverage of magnetism in this class is what's the sort of the basic unit of interaction with magnetic field, which we are going to say we have it somehow. And in next Wednesday's class, when I'm getting evaluated, that's when we are going to talk about the fundamental source of magnetic field. For today, we'll say we have magnetic field somehow. I mean, we know where to find the magnets. Here's a magnet. So I know how to get my magnetic field from a permanent magnet. And for today, we are simply going to say, all right, how does this magnet interact with some other fundamental entity so that we can base all our understanding of magnetism on this. So we are going to start by saying these magnets, they're not fundamental because sort of, it's macroscopic object. And so this is not the fundamental object. And if we try to get down to this level, field interacting with the charge to produce a force, well, we don't have magnetic charge. So this is a very puzzling thing. And unless someone here happens to know the answer, what's the elementary object in nature that does interact with the magnetic field? Yes, no? So I will reenact one of the experiments that were done in the, I guess, early 19th century. It's I have to imagine it was an accidental discovery. Actually, the accidental discovery, it happened the other way. People were observing the interaction with magnets with this other thing, but I don't really have the tools to demonstrate that. So I'm going to demonstrate the flip side of that interaction, where you have a strong magnet already, and something that you can describe as in terms of some fundamental object, elementary object, interacts with this magnet. So right now, I have this magnet here, and let me move this camera so that you can see it better. This is some setup I have with the wires and whatnot. So when I move this magnet around, you don't see any interaction with this wire, right? And does that sound like that's what you would expect? Yes? Yeah, wires made out of copper. Key thing is that it's not ferromagnetic. I forget if it's diamagnetic or paramagnetic, but whatever it is, it's a very weak interaction. That's why you are not seeing any force. When I move this, you don't really see any interaction here. Yeah? Now, so that's true of copper wire and just a magnet. But what happens is, let me turn on this power supply. Can everyone read that it's outputting zero current? Right? So what I have here is I have wire, the black wire here connected to the negative terminal. And I have this red wire connected to the positive terminal. And I have this end open so that I can briefly touch it to let current flow. So let's see what happens. Oh, maybe I moved the wire. Oh, that's why I taped it down here. I want you to make sure that I don't accidentally move the wire. Let me just tape it down one more time to make sure that when I'm touching that end, you have some reasonable assurance that that's not what's moving the wire. So, all right, tape it down one more time. So, even though I'm moving this, okay, that shouldn't move the other end. All right. Now, let me touch this end. So I guess you can't really see it in the camera, but when you look at the screen, you will see this portion of the wire suddenly move. Then that matches with when the current starts to flow. Like, that number, it goes from 0 to 3. That's sort of the maximum current my power supply can provide. So when it has 0 current, nothing happens. When the current starts to flow, then the wire suddenly moves. And what's more fun is I can change the directions. So let me take this magnet and turn it around. So, I don't know which end is North Pole. Probably should have figured that out. Is it moving in the same direction it did the last time? No, it's moving the other way, right? So, so any guesses? How would you describe the elementary object in nature that interacts with this magnetic field that's coming out of this magnet? Electrons. The electric charges are somehow interacting with this magnet. Now, it doesn't interact all the time, as you can see. Right now, it's not interacting. It's not doing anything. It interacts only under certain circumstances. So let me do a couple things to describe them more carefully. I have to kind of label this. The blue is the North Pole, right? Let me see. OK, so this is repelling the blue end. So this is my North Pole. Let me write N on it. OK. Double check. All right. So this is my North Pole here. Let me do this experiment one more time. So yeah, you kind of to imagine that this is your right hand or left hand side and the right hand side. So when I let the current flow, then it jumps over to that side. All right, so let me try to draw this picture on the board. So I have my North Pole here, which produces magnetic field that I'm going to illustrate this way. And what I have set up is I have set up a current that flows from left to right. So I have a current that's coming in, flowing through. So if we insist on describing this as some sort of interaction with the electron, which direction is electron flowing? Left to right or right to left? Once again, so I'm describing my current as flowing from left to right. Yeah, because electron is negatively charged. That's the convention. That's just the convention we have to deal with. So what this means is I have electrons that are moving from right to left, according to the description we have. So, so I have two kind of things that are describing some sort of direction. Magnetic field pointing up, and I guess electron velocity pointing to the left. What direction is my force? Based on what you see here. Does the wire jump up or down? Does it really jump up? Jumps sideways, right? So it's not really jumping up. In fact, let me do this. I can change the direction of current instead. So if I just flip this around here, then I can change the direction. Wait, can someone remember which direction the wire went? Okay, came towards me, right? So when I flip the direction of current around, then it goes the other way. But in both cases, it goes sideways. It doesn't go up or down. So, all right, it's going sideways. Is it going in the same direction as the direction of this electron velocity? No, because if it's going in the direction of the electrons moving, it would get pulled or pushed this way, right? But that's not what it's doing. It's going perpendicular to that direction. So on this board, let's be careful. So we are saying this is left and right. And you're kind of looking at the board. So the direction of the force, is it into the board? Or, yeah, it's into the board, right? Yeah, so that's the direction of the force you get. In this picture, yeah, right? So this is left to right. Wait, so I need to flip it around. So if I'm drawing it, yeah, so if, let me do it another way so that, let me arrange this in a way that from the way you guys are looking at, the current is flowing from left to right. So this is the positive end that, current comes out over here, flows through here from left to right. So when the things are set up that way, current, the wire gets pushed that way. So the force in this case is coming out of the board. Okay? So in this picture, this electron, as it flows through, you get the force on that electron is out of the board. Okay? So this is what I mean, magnetism is complicated. Even trying to figure out the direction of magnetic force, well, it doesn't go in the direction of the magnetic field, apparently. if you're trying to describe the elementary interaction of the magnetic field with the electric charge. And one of the things that seems to affect whether there's magnetic force or not, oh, let me put a little symbol. B is the letter we use for magnet. If the electrons are not moving, if there's no current, then there's no magnetic force at all. So having this charge moving must be an important part of it. And when you get there to be a force by causing current to flow, then the direction of the force once again doesn't seem to have anything to do with the velocity, because the force is not going in the direction of velocity either. If it was has something to do with the velocity, you might be able to get some sense of intuition using friction force. Friction force usually goes against the velocity, but it's nothing like that here either. So it comes down to we have to somehow relate the. So we are trying to describe the elementary interaction here. Somehow this magnetic field, which points up, and this velocity vector, which in this case points to left because it's negative charge flowing to the left. Somehow I have to be able to combine these two vectors to give something that's coming out horizontally out of the board. Have you seen any mathematical operation or description that gave you this kind of description? You have two vectors, one pointing up, one pointing to the left. And by combining these two vectors, you have something. How would you describe the direction of this vector relative to these two? Yeah, you skipped a couple steps. How would you describe the direction of this vector to these other two vectors? Perpendicular, right? That's what you're saying. Okay. Why are you guys whispering? So perpendicular. So this vector is perpendicular to both the magnetic field and it's perpendicular to the velocity. And as Crystal was saying, one kind of mathematical operation that gives something that's perpendicular to both of the inputs that are going into it, and that's cross product. So this is going to be how we describe magnetic force. So magnetic force, the very basic expression for magnetic force is, so we are describing force due to a magnetic field on some kind of charge. And it's not going to depend on just remember this is electric charge, not magnetic charge. It doesn't just depend on the charge. It also depends on the velocity, what kind of velocity it has. And I guess if I'm being complete here, it also depends on the magnetic field. So the equation for this vector force is going to be electric charge times V cross B. The velocity vector cross magnetic field. And that's what you are seeing here. I have set it up so that current goes from left to right. And from the cross product, current cross the magnetic field, force goes that way. Wait, but isn't the velocity pointing to the left? If you're doing cross product of V cross B, doesn't that go into the board? Why does force come out of the board? So you are saying that if instead of we had this electrons, if we had a positive charge that's going in the same direction of current, then that would make sense, right? But is this what we really have? No, this is what we really have. So we want to make sense of this expression using what actually does happen. By the way, before maybe we go into this today, how many people need a review of cross product and right-hand rule? Yeah, fine, most people do. We do cover it in Physics 4a, but for some of you, it's been a while, and for many of you, the first time. So one of the things that all of this tells you is that to describe magnetism, magnetic force, you need the full 3 dimensions. So everything we have done up to now could have been done in 2 dimensions. We draw electric fields in 2 dimensions, we draw equipotentials in 2 dimensions. But once you get to magnetism, you have to come face with the fact that we live in 3-dimensional world, and there's no way to describe this phenomenon without using all 3 dimensions. So let's wrap it up here. So what we observed experimentally was that as the current flows left to right, is this still on? Yeah. As if the current flows from left to right, the force on the wire is it pushes it out of the board. All right. So let's try to reason it out through here. So when I do V cross B, what direction does the V velocity cross the magnetic field B go? It goes into the board, right? So I have to explain why the force comes out of the board. Why does it come out of the board? Because of this charge. Electron charge is a negative charge. So, this charge here is minus E, not plus E. So, because it's a negative charge that's moving. So it's the same thing you had with electric fields. In fact, I would tell you that this particular combination here, this is more similar to electric field than anything else is. The quantity of V cross B is the quantity that you can almost compare directly to electric field. And we'll talk about that more later. Now, what if, so you could say the thing about us assigning negative charge to the electron is an accident of history, right? So when I describe my current this way, it could have really been a positive charge that's moving to right. In that case, do you get the same result when you describe the force? So V cross B points out of the board, but this time my charge will be positive. So with this, it'll be positive E. So yeah, when you're looking at force, it doesn't matter if the moving charge is negative or positive. So that's really that's a sort of semi-justification of what I said earlier when we were doing circuits. That often we pretend that the current is a positive charge moving in the direction of current, because almost always that doesn't matter. Even when we are dealing with the magnetic force, it still doesn't matter. The direction of magnetic force is the same, whether we are describing positive charge moving with the current or negative charge moving the opposite from current. The one exception that you should know is something called the Hall effect. If we have time today, I think we'll have time today, we'll describe something called the Hall effect. That is a one exception where the actual sign of the actual charge carrier does matter. Hi, this is a lecture video on right-hand rules. I wanted to use this lecture as an opportunity to highlight the conceptual ideas behind the right-hand rule procedures. So the right-hand rule is what you use when you want to associate a direction with a plane, with a planar quantity, if you want to associate a vector-like direction. Let me demonstrate what I mean by using this 3D design software, Autodesk Fusion 360. So let me draw a planar object first. I'm going to create a plane out of this object. So I have this planar object, and let's say I wanted to describe its direction. I could do it by what plane it's on. Here you can see that it's on that XZ plane. But for an arbitrary direction of the plane, that becomes not possible. So the right-hand rule is what we use to specify that direction of the plane. Now, you might remember from your geometry that when you have a plane, there is actually a unique direction that you can associate with that plane. And that unique direction can be described by a line perpendicular to the plane. Now, I have this little circle in the middle of the plane, and I can use this to show what perpendicular to the plane looks like. This is perpendicular to the plane. And as I rotate around, you can kind of see what it looks like. That hopefully fits with what you thought of as being perpendicular. Now, if we simply say we associate the direction of the plane with the direction that's perpendicular to the plane, that rules out an infinite number of possibilities that we had before. But it doesn't go quite far enough, because when you are talking about perpendicular directions, there's this upward direction, and there can also be this downward direction. And in some applications, you won't care. And that's the cases you saw in geometry. In geometry, if you have a plane, you can just associate a line with it. Line doesn't have a sense of direction. I mean, not up and down direction. Line just marks that axis. And you are done. Now, often in physics, you do care about that up or down direction. That's what vectors are. It's an arrow. So we need a rule to distinguish between these two directions. And that's where we introduce right-hand rule. Right-hand rule allows you to pick out between two perpendicular directions of the plane. Should it be one that's perpendicular in one way or one that's perpendicular in another way? And as long as we are consistent about it, we could have chosen one set of rules or the other set of rules, and both would have been fine, as long as we are consistent about it. And I guess what I'm trying to say is we could have used the left-hand rules and formulate all of physics that way, and that would have been perfectly fine. But 90% of us are right-handed, so right-hand is easier for 90% of us. So that's why we use right-hand rule to enforce one consistent set of rules, so that when we talk about, for example, direction of magnetic field, that we all have the same direction in mind, given the electric current that produces that magnetic field. So let's go over some of the right-hand rules you have in the textbook and see how using the right hand applies to give one unique direction out of these two potential perpendicular directions that could have been chosen. So this is the first right-hand rule that's in the textbook. And here you can look at the vector v, the velocity vector, and the vector b, the magnetic field vector. And these two vectors, they define a plane. And that's the plane that you see drawn on this diagram here. And for the purpose of our discussion, let's say this plane is the plane of the screen. The drawing is drawn in a perspective view, but let's say this is the plane of the screen. Then what the right-hand rule says is, well, you align your hand. So when you look at the textbook, the force is given as the charge times V cross product with B. Here the order matters. V is the first vector, B is the second vector. So if you have a plane defined that way using two vectors, one first vector and another second vector, then what the right-hand rule in the textbook says is take your right hand, align the thumb of your right hand so that the thumb points in the direction of the first vector, then orient to your hand so that the rest of your four fingers are oriented in the direction of the second vector, then the direction your palm points out in, as if you're pushing in that direction is the direction that you want to associate with that plane. So V cross B is or Q times V cross B is equal to force, the direction of force vector F. So that's the right-hand rule. By the way, this isn't the right-hand rule that I learned when I was in school. I learned a different one. Let me just quickly show those two in case you see them as you're looking at different books. The common one that you might see in different books is the three-finger version. Now, I actually don't like this one, and you will never see me use it, but I will just use it this once to demonstrate it. So these three fingers represent the direction of the three vectors. These two will be the vectors you use to define the plane, and this will be the direction you associate the plane with. So this finger, index finger, you let it point in the direction of the first vector, and the middle finger, you let it point in the direction of the second vector, B. So I have this V and B in the plane of the screen that you see. Then the thumb points in the direction of the cross product third vector, or the direction you associate with the plane. So it's pointing out of the screen, same as the one you saw. The one I personally use, the one I like, it's a whole hand version, and you will see why I like this one when we get to the shortcut right hand rules in the next two screens. So in this one, I orient my hand first in the direction of the first vector. So in that case, in the direction of V. And then I orient my hand until I can bend my fingers in the direction of the second vector. That would be B, which is pointing up in the plane of the screen. So, okay, I have to orient my hand this way. Then I can bend my fingers from the first vector V to the second vector B. So that's what you see, V cross B. Or these two directions are the directions that, these two vectors are the vectors that define the plane, and my thumb points in the direction of F, or the direction that we want to associate the plane with. V cross B is equal to F. So these are the some versions of right-hand rules. The version in your textbook is perfectly fine. It's great. It in fact highlights the fact that you are associating a plane with a vector. So I think in that sense it's conceptually an excellent one to use. Just make sure that you use your right hand. Don't use your left hand, because your left hand, it's called right hand rule. So both of these two directions could have been equally good. Direction that points out of the screen versus direction that points into the screen could have been equally good. The only thing is we had to be consistent. And since 90% of us are right-handed, we are choosing the right hand to let us be consistent with that one convention we have chosen. So that's the first right-hand rule. I would say this is the fundamental, elementary, basic right-hand rule. The rest are kind of a shortcut right-hand rule that kind of bypasses all the complicated math that we might do in a more mathematically based physics class. So let me show you those two shortcut rules that could be very useful. So here's one shortcut rule. This is probably the most applicable, useful one. It associates the direction of current with the magnetic field that's generated by the current. So this is the physical picture that you have. Current flows in one direction, and that generates magnetic field that's going in concentric circles around the current. And so if you position yourself so that you look at current that's coming towards you, you would see those magnetic fields going counterclockwise. That's what you would see. And the shortcut rule that you can use to help you remember that is this one. So you use your right hand. Once again, it's a right hand rule, not left hand rule. You point your thumb in the direction of the current. Then what the right hand rule says is that the direction that your fingers curl in, that's the direction that those circular magnetic fields curl in. So if you look at this thumb from above, then the fingers will look like they're curling in the counterclockwise direction, and that's what that picture is showing. That with the thumb pointing in the direction of current, the direction the fingers curl in is the direction of magnetic field. Now, you can arrange electrical currents in different geometric arrangements to produce more useful magnetic field than the ones going in circles. That's where you see the other shortcut right-hand rule. So I don't think your textbook explicitly gives you this as a shortcut right-hand rule. So let me just point out the connection. So the first thing you do is you use the right-hand rule that we went over just now. You point your thumb in the direction of current. Then the direction your fingers curl in is the direction of magnetic field. So when you do it at the locations shown in the picture, in the far part of the segment, on the right side of the segment, and then on the close side of the segment, then what you see is that inside the loop, the magnetic field all points up. And that's what the diagram here shows, and that's what the diagram here shows. And now this is the shortcut rule I like to use in a circumstance like this. You say, well, I'm going to, using my right hand, I recognize that the currents are going in circles, so I'm going to use my fingers to go in that circular direction. Then the magnetic field inside the loop, which is mostly straight, as you can see here, that straight magnetic field goes in the direction of the thumb. So these currents, they are oriented in such a way that if you look from above, the current is going counterclockwise. So you let your fingers curl in counterclockwise direction, the magnetic field is coming towards you, pointing up. If the current was going in the other direction, then you orient your hand so that the current goes clockwise and magnetic field will point away from you. So that's the right hand rule. It's a way to use your body part to remember which convention that 100% of physicists, even the left-handed ones, agree to go with. So for the purpose of our class, Physics 10, you will see in your homework that this right-hand rule is not hugely emphasized. It's because, it's complicated. We really stop at the conceptual level of when you look at magnetic force, for example, that the magnetic force is perpendicular to both the magnetic field and the velocity of the charged particle. That's the main point that I want you to get. But some of you are going on to next level of physics, the ones that are more mathematically based. There, you will have to master this right-hand rule to do magnetism correctly. So that's what this lecture is for. I think I have one application of this right-hand rule with actual physical demos. So watch out for that video. Until next time, bye. Magnetic force on a current carrying wire. That's all fun and fine. You see something that's moving, that's clear enough indication that there is a force on something that's good. And what I want you to show here is a cleaner demonstration of magnetic force on a moving charge in a way that you can quite clearly see it without any, complications or whatever. Okay, let me show you this magnetic force lab cyclotron motion. Yeah, so in this video, we will measure the cyclotron motion applying different amount of accelerating voltage and magnetic coil current. This is the first video using the apparatus 1. The electron beam is on right now at the maximum accelerating voltage, but it's not visible because the room light is too bright. Let me darken the room. All the lights are off except for the one torch flashlight on the video camera that's recording the voltmeter and ammeter. So this is the electron beam. This bulb is filled with a little bit of, I forget what gas it is. It might be argon. And as the electrons collide with the gas in the very thin density of gas, it produces this light, which is how you can see the electron beam path. Right now, it came out of this thing, accelerated, and it's going in a straight-ish path. We'll turn on the magnetic current, first in the clockwise direction. And let's see what the minimum value of current is. That'll give us a circle. About 1 ampere, so we will set it at 1 ampere. Now so that's the cyclotron motion. So this curved beam path you see is the result of the magnetic force on a moving charge, which is described through the right-hand rule, and and yeah, you get a circulating charge. Well, they don't really circulate; they end here. They strike something, and then they're done. But this is kind of clear, very clean illustration of magnetic force. And let me just play a little more of the video where we go through some variation of parameters. Rotating the Lorentz tube, making sure that the beam returns to itself rather than undergoing a helical motion. And we will increase the magnetic field by 0.2 ampere increments. This is 1.2 ampere. 1.4 ampere. And this smaller radius loop indicates the magnetic force, the force that's providing the centripetal force, is stronger. And it's stronger because the magnetic field is greater, and the magnetic field is greater because the electric current on this outside the Helmholtz coils that's producing the magnetic field, the electric current is greater. 1.6 ampere, and so on. For measurement, please pause the video so that you can make the measurement of the diameter of the circular path. Two rulers are shown on screen so that you can calibrate the scale. Please be mindful of perspective effect. The circular path is at about the midpoint between the two rulers. Okay, the rest of the video, so I do vary this accelerating voltage, which varies the velocity of the electrons coming out, but I don't think I recorded this in a way where you can clearly compare the effect of different velocities more easily without doing all the data taking and all that. So let me not play the rest of the video, but this is the kind of clean representation of magnetic force, illustration of magnetic force. And I want you to show one more thing. It's something called the crossed field setup. Well, let me just play it in and show. This is a setup that involves both magnetic field and electric field. This is the crossed fields measurement using apparatus 1. This technique can be used to directly estimate the velocity of the electrons. Please note the precision of this technique is limited for a number of reasons. I am overlaying a white line here to indicate the undeflected path of the beam. Brief explanation. As I turn these knobs, I'm going to be applying magnetic field like before, causing the beam to bend. And what one of the other knobs about deflecting voltage is doing, it sets up a voltage difference between these two plates. And that sets up an electric field between these two plates. So the fields that point mostly in the vertical direction. Now, as I apply the deflecting voltage at the maximum value of 250 volts, so what this is showing is that this is a beam of electrons. So this top plate must be charged positively, attracting the beam, and the bottom plate must be charged negatively. That results in electric field pointing downward, and on a negative charge, that downward pointing electric field pushes it upward, the electrons upward. The beam path is deflected, and we will apply magnetic field with the current in the counterclockwise direction to deflect the beam back. Please pause the video where you see the beam at the location of the undeflected position and read. And this is where people doing the actual experiment kind of have to be careful. Electric field is very highly localized here, and magnetic field is all over this entire space. So you have to be careful to note, okay, in this region, they're kind of canceling each other's effect. the magnetic force is tending to bend the beam downward, downward everywhere. But the electric force in this region is tending to push it upward. So within this region, you can find a place where the effects of the two fields are kind of balancing each other out. And with more math, you can relate those magnetic and electric field values directly to the velocity of the particle that's passing through undeflected. The current value there for the measurement of magnetic field. I think that was all the interesting thing I would say about this. That would be around this position. Yeah. Please note that outside of the region between the electrodes, the electron beam will continue to bend under the influence of magnetic field. So you only have to look at the region between the electrodes. Right. I think that's enough. In fact, we're way over time. So those are the videos I want you to show. I guess that is the end of this playlist. In this lecture, we will look at the geometry of magnetic fields produced by electric current. I mentioned some of this in the right-hand rule lecture. This is the textbook's shortcut right-hand rule 2 that relates the straight electric current with the circular magnetic field produced by the straight electric current. So here, if you imagine the current in the conventional direction of current flowing upward, the direction of thumb, then the magnetic field that upward straight current produces can be visualized as the direction in which the 4 remaining fingers curl around. So this notebook LM infographic already drew those circles. I think it has arrows, but they are not very visible. So on the side of the circle that's near me, it'll be going from left to right. On the side of the circle that's farther away, it'll be going from right to left. And on the left side of the circle, it'll be pointing out of the screen. On the right side of the circle, it'll be pointing into the screen. So that if you imagine your right hand, thumb pointed up, then as your fingers curl around, on the right side of that straight wire, right side, it's pointing into the screen, curl around, and on the left side, it's pointing out of the screen. And we imagine those magnetic fields as concentric circles. Direction-wise, they are all kind of pointing in the same circular directions. Now, we refer to this as the shortcut right-hand rule. So you might be wondering what's the original version, one that's not a shortcut. So this goes to a topic that we don't quite cover in this class, because you need to use something called the Biot-Savart's law that tells you small contribution to magnetic field that comes from small current segment. And it's a very complicated looking law. I'll just write it down, but you don't have to know it. The small contribution to magnetic field is equal to, there's a constant here, what's called the permeability of free space, divided by 4 pi times. For handling the magnitude and direction, we separate out this di, infinitesimal current element, as this, the amount of current I times the infinitesimal section of the wire, dl. And I think we put all the directional quantity on the dl, the wire segment. So the amount of current that doesn't change along a straight wire times dl, which I guess also doesn't really change along a straight wire, but this also applies to a curved section of wire. And then this is the mathematical bit. To get this vector quantity dB, you have to say you get the vector quantity on the right hand side by dl vector cross product with r hat, the displacement unit vector. All of that divided by r squared. It's still an inverse square law like Coulomb's law. It just looks a little bit more complicated than Coulomb's law, which is while we do cover Coulomb's law when we do electricity, we don't cover Biot-Savart's law. I thought about covering it, but I think it's gonna be too complicated. But for those of you who are interested, I keep saying this right-hand rule 2 is a shortcut rule. Where do you get the original rule? You get the original rule by using Biot-Savart's law, and within Biot-Savart's law are these vector quantities. The small contribution to magnetic field that comes from two vectors, dl and r hat, and this cross product. That's where you use the other original right-hand rule that you have seen me cover. Your textbook has that version with you use your thumb and the index finger as the first and the second vector, and the direction in which your hand is pushing is the direction of the cross product. Or your textbook puts it in the context of the direction of magnetic force. And I gave you two other versions, one using 3 fingers, and the version I like using the whole hand. So dl is the direction in which you orient your finger, and r hat is the direction in which your fingers curl. Then your thumb is the direction in which your cross product goes. And applying it here, it's again complicated, so I won't go through that. But for those of you interested, this is what you would look up, Biot-Savart's law. Now, let me look at a couple simple applications that you will see conceptually in this class. There's the example with the circular loop, and this infographic isn't quite complete in terms of specifying in what direction is the current is flowing. It must be flowing in this direction for the direction of the permanent magnet that they placed to make sense. So let me make sure I draw this direction of current. Then you can actually imagine applying the right-hand rule number 2 to this circular loop, little segment at a time, like this little section at a time. Then you have thumb that's going in that direction, and your fingers are curling like this. So inside the loop, you can see the magnetic field is pointing in, and outside the loop, magnetic field is coming out of the screen. So the magnetic field due to that little segment would look something like this circular kind of contribution. And you imagine doing it all the way throughout, then I think at each section that you might analyze, what you are going to get is, so with the direction of current going that way, inside the loop, magnetic field is again pointing in, outside coming out. So you imagine going through like that. Let me just do one more here for representation. Then so the current has looped around, and now it's coming this way, and again now this is the outside. Outside it's pointing out of the screen, and then inside it's pointing into the screen. And in this perspective view, I think what you should imagine is rotating this loop around just a little bit, so that this near side where current is flowing up is so that the loop looks like this. If the loop looks like this, so that this near side is going up, and then after having turned around on the far side, it's coming down. So at the top, the current is pointing into the screen. After this loops around, at the bottom, current would be pointing out of the screen. In that view, within the loop, the magnetic field is pointing from right to left. And that's the direction of the magnetic field you would have if you have a permanent magnet with the north pole pointed to the left. That's the way in which I figure, the current must be oriented this way, so that the direction of magnetic field makes sense with the direction in which they place the magnet. And this gives the other shortcut right-hand rule. So when you have a loop of current, what the shortcut right-hand rule says is, so let me curl my fingers so that it matches what I drew here from your perspective. So on the side that's closer to you, the current is pointing up in the screen, so that at the top it's going to point into the screen, and then it's going to curl around, going down on the far side, and then the current will point out of the screen. So if you orient your right hand, so that you can do that, then your thumb points from right to left. And that's the direction of the magnetic field. So if you have a circular current that results in a straight-ish magnetic field inside the loop, and that points in the direction of the thumb. If you orient your right hand so that your forefingers follow the direction of the circular current. So that's I don't think your textbook numbers this right hand rule, but this would be, I don't know, right hand rule number 3. This is one of the shortcut rules that tells you from one of the relatively common direction of the current in what direction the magnetic fields would go. And this is a useful arrangement. You can come up with a situation that's actually pretty practical. I think solenoid geometry is one of the geometries that your textbook also gives. By the way, these formulas, I wouldn't worry about it too much, other than this is something called the magnetic constant, or I guess permeability. So if it's mu naught, it's a permeativity of free space, and I'll mention how that relates to what's on the right side of the screen. So here, I think for the let me imagine the direction of the current, so that magnetic field, when I'm done figuring out the direction, it'll be coming kind of to the left side, inside the solenoid. For that direction to make sense, I need to have current here on the right or the far side of the solenoid that's going up, and then from there it'll just follow the direction of the wire, kind of loop around like this, and then keep going, and after looping, and I'm not sure if how the AI drew this ending. I don't think it quite makes sense. So let me just scratch this out, and I'll imagine after looping and looping, and then on this far side it'll just continue to go straight down, and that is the direction of current. So if this is your direction of current, then again, using your right hand, imagine you're at the far side with the current coming up, then as it loops around, so your thumb is pointing kind of from right to left-ish, and this is the direction of the magnetic field. That's the inside, and with the solenoid, that particular geometry works out so that outside magnetic field is approximately 0. That is something that we don't quite get into, and again, the formulas, I think this formula is from the textbook, but I won't ever really ask you about it, so you don't have to worry about it. So I'll just say no worries about formulas. So this would be another application of the second shortcut right hand rule, where your forefingers curl in the direction of the looping current, and there can be many loops like in a solenoid, and inside that loop you will have straight-ish magnetic field that follows the direction given by the shortcut rule. And what's on this corner here, this relates to something that's a little bit different, but your textbook does cover it with ferromagnetic materials, and I think maybe with the transformers. It does come down to this particular formula with the permeability of free space, or the magnetic constant in vacuum, that applies for when your coil encloses nothing, like vacuum, or air is pretty close to vacuum when it comes to magnetism. So this applies to this. Now, in many applications, there's an advantage to having large value of permeability. So let me say advantages to make large. Whether that's building a transformer or a circuit component called inductor. So the way you can make this constant larger is by having a different material within the solenoid. So a ferromagnetic material might have a magnetic permeability that's on the order of something like, I don't know, like a 10 to the 4, or I guess that would be like 10,000. So if you're dealing with any of the other two types of magnetic materials, whether paramagnetic or diamagnetic, it's going to be a tiny correction from the vacuum permeability. But if you are dealing with ferromagnetic materials, you can have this constant to be many orders of magnitude larger. And that makes your inductors more efficient, your transformer more efficient. It allows you to create larger magnetic field out of smaller amount of current. So I think that's all the examples your textbook covers. And within this infographic, actually, there's a little bit more material, but I don't really want you to worry about these formulas, so let me not really talk about it. But I did want to give you an example. So let me give you this example. Let's imagine that you are dealing with long straight wires. Let me go over here where I can have more room. So if you have two wires, let's say with a current that's flowing parallel to each other in the same direction, then you can work out the magnetic force between these two wires. Let me number them. So this will be my first wire, this will be my second wire. Then this first wire, with my thumb pointed in the direction of current, it'll generate magnetic field that goes around like this in kind of circles. Let me draw a few circles of different diameters. Just gonna draw out to the second wire. So with my thumb pointing up, so on the far side it's going from right to left, and so on the far side going from right to left, on the left hand side coming out of the screen, on the closer side going from left to right, on the right side going into the screen. So that's the general direction of magnetic field from this current, or one current. And at the location of wire number 2, there is magnetic field, and there's a magnetic force, or force due to magnetic field, on a current carrying wire that goes as amount of current, length of the current, cross product with the magnetic field. And when you focus your attention to this portion where you have magnetic field at the location of current with the current flowing up, then you can go through the right hand rule again. So your textbook's version would look like where you orient your thumb in the direction of first vector. That would be in the direction of current, IL vector. And then you orient your fingers so that the rest of your fingers are in the direction of the second vector. That's in the direction of the magnetic field. That's pointing into the screen, so it would be like this. Then direction your palm appears to push in is the direction of the force. So from right to left. So magnetic force law says there's a leftward force from this magnetic field on the current carrying wire. And my version of the right hand rule is you orient your entire hand in the direction of the first vector, IL, and you orient it until you can bend your fingers in the direction of the second vector, that's a magnetic field pointing into the screen. Then the direction of your thumb is in the direction of the cross product, or the magnetic force in this case. So that's from right to left. Same direction whether you use textbook's rule or mine. And what this is saying is that if you have two lines of current parallel flowing in the same direction, then there's an attractive force. So I did the analysis of force of wire 1 on 2. And if you do a similar analysis of the field due to 2 on 1, then you will find that the direction of the force in that case is to the right. So either way, it's still an attractive force. And I forget if I ask you questions like this, but this is something that you could almost memorize as a rule. If you have a parallel lines of current, then the force between them is attractive, which on a quick sense looks kind of opposite of the other rules you had. With the charges, we had like charges repel, opposites attract. But with the currents, the same direction currents will now attract, and the opposite direction currents, if you go through the analysis, you will find that they repel. just works out that way. Okay, so that's probably enough. So this is the lecture on magnetic field geometries, and again, the whole quantitative approach to it, the way we might do it in physics 4B, it's too complicated, involves too much math. So as you will see with the rest of the lectures, it's mostly heavy on demonstrations and conceptual understanding. And I do want you to at least understand the directions of magnetic fields produced by a couple example geometries of electric current. Thank you. Bye. Oh, before I move on, I should talk about unit of magnetic field. How many? Because I never really talked about that yet. So how many here know the units of magnetic field? There's two common units that are in use. How many here have dealt anything with the magnetic field? No one here? Okay. But some things you might know. So let me write down first. Unit of magnetic field. Well, what are some of the common magnetic phenomena that everyone around the world can refer to? There's got to be something. Okay, that's why does aurora borealis happen at all? Because you wouldn't see aurora borealis on Mars or Venus or Moon. It happens only on Earth. Of all the planets in the solar system, it happens only on Earth, and maybe Jupiter. But why? Well, but Jupiter is a gas giant. It's not a okay. Of all the terrestrial planets, it happens only on Earth. So why does it happen on Earth and none of the other rock planets?
Waves coming from the sun.
There's the geomagnetic field. There's magnetic field due to the Earth. That is something that everyone can refer to. So that would be a convenient magnetic field to refer to. And this is the unit that's convenient for referring to how much magnetic field does the Earth have. That this is like the customary unit. So we call that gauss. Gauss is one of the convenient unit of magnetic field, named after the same guy that Gauss's law is named after. He was, he did a lot of stuff. So Gauss is defined in such a way that the Earth magnetic field due to Earth, it depends on where you are on the Earth. The strength varies a little bit. It's dipole field pattern, and it depends on where you are. But it's going to be approximately 0.5 Gauss. So, this is a respectable amount of magnetic field. It's large enough that it affects this compass, right? So I'm not talking about some microscopic amount of magnetic field. It's enough that, wait, did my compass demagnetize all again? Yeah, I think it's fine. It's going to point to north. Okay, so it's a large enough magnetic field that it'll affect compasses. All right. The downside of Gauss, so if you work with any kind of magnetic field, you'll see Gauss a lot. It's a very convenient unit. When my research used to involve magnetic fields, this is the unit we used all the time. But this is not an SI unit. As in, the promise in SI unit is that when you stick to SI unit, you will get really simple quantity. For example, you have this expression here, right? The promise of SI unit is that if you use ampere and meter and on SI unit here, then promise is that when you multiply this out, you are going to get Newton. That's the whole reason we have SI unit. And if we use the Gauss here, that wouldn't work. That wouldn't give you Newton. In fact, it'll give you 0.1 millinewton. So Gauss is not an SI unit. It's based on an SI unit, but the actual SI unit of magnetic field, it's some other one, that name that you probably have heard before, Tesla. So Tesla is the SI unit of magnetic field. And the way to get a sense about Tesla is that it's related to Gauss this way. 1 Tesla is 10 to the 4 Gauss. Does Tesla sound like a small or large magnetic field? Large, yeah. And do you guys know how to generate huge magnetic field artificially? Well, yeah, so something like electromagnet, like the place that uses really large magnetic fields are like a CERN, the Large Hadron Collider. Anybody here know how those electromagnets are made? They use something called the superconductors to make as much current to flow as possible, because looking at expression like this, the more current you have, the more magnetic field you can have. And I keep forgetting, I think the largest magnetic field that we can produce is something like 40 Tesla. Is that right? It might be 15. I don't know, it's definitely less than 100 Tesla. So Tesla is such a large unit of magnetic field that if somebody ever tells you about they have 100 Tesla magnet, you know they are lying, because there are no materials with the properties that can produce that large of a magnetic field. So these are the units of magnetic field. Let me just wrap it up with this one last thing. So if a Tesla is an SI unit, so I'm saying that if I plug in Tesla here, that all the units will work out so that I get a unit of Newton here. So this is not one of the basic SI units. It must be related to the basic SI units somehow. So how is it related? Or how would you get at it? I mean, you could always look it up. You could say, all right, what is 1 Tesla? And Wolfram alpha will be able to tell you. That's one of the nice things about Wolfram alpha. It's unit aware, and whenever you give it a physical quantity, it actually expresses in many different ways. So 10 kilogauss. That's what I was saying earlier. This is how I memorize, get a sense for Tesla. But if you keep going down, okay, here it is. Basic unit dimensions. It says mass per time squared per current. Oops, what did I do? Mass per time squared per current. So kilogram per second squared per ampere. So if you have access to Wolfram alpha, that's all great. You would just look it up. How would you figure this out? What did I tell you about remembering units in the electromagnetism? I told you it's complicated, that I don't try to. When we are doing circuits with a volt, ampere, ohm, that's when I was telling you there's sort of interlocking web of relationships. I don't really try to memorize any particular unit in terms of other things. It's something that you're just going to end up forgetting. But there's something that I do try to remember. Well, I guess 2 things that I try to memorize. Let me tell you the first thing I memorize all my formulas. So, everything I write down here, I can write it down from memory. How would this help me figure out units? So once I have this formula where I know all the units, then whatever Tesla is, it must be defined in a way that the algebraic relationship here is valid. That's the whole principle behind dimensional analysis. So once I have remembered the formula that relates the quantity I want in terms of other quantities that I already know the units of, then I can go back. I can use this formula to figure out what Tesla is in terms of these other things. So let's just quickly do that. It won't take that much effort. So it'll be, okay, force, Newton is equal to ampere times meter times Tesla. By the way, when I do these notations, I have to tell you, I do it slightly non-standard. The standard way is actually to write these out using symbol M for mass, T for time, and current, I guess I for current. But I found that to be confusing to a lot of people. So I'm just going to use symbols for SI units, because the assumption in this class is you're not going to go away from SI units. So solve this for T, Tesla. then you get Tesla, or rather 1 Tesla is equal to 1 Newton per ampere times meter. Hey, that's not what I have there. But I can write out what a Newton is. Hopefully you have this memorized. Newton is equal to kilogram times meter per second squared. Now, if you don't have this memorized, how would you get at that? What would you try to remember to recall that this is the relationship for Newton? Yeah, Newton's second law. Net force is equal to mass times acceleration. So this is force is equal to mass times acceleration. So the technique I'm telling you could have used it from physics 4a. It's just that only with the electricity and magnetism, unit relationships become complicated enough that if you're trying to memorize this, you'll forget it. But if you memorize this, you will always be able to rederive this. So anyways, putting this in, so it's a kilogram, meters cancel out, so I end up with 1 kilogram per second squared times ampere. And that's what you have there on the board. And I can do one more check. I guess it's a sort of unnecessary, but maybe it's useful. So this mu naught, I have it expressed in terms of Newton per ampere squared. But this kind of obscures the fact just how important this permeability constant is in expressing magnetic field, right? So let's say I want you to express this mu naught, not in terms of Newton's forces and current, but in terms of how much magnetic field is going to be produced. Then I do the same thing here. I write down, all right, this is a formula that I have memorized and can use. There are other formulas that I could use, but this will work as well as any other formula. So, or if I don't have this handy, I could go back to this. But this is simpler. And the key here is that to have a recognition of the algebraic relationship that's expressed in the formula. It's the same algebraic relationship for the unit. So once you start paying attention to this, units will just come automatically. It's not something you have to put in a lot of effort into memorizing. So let me just write that down. So I have one relationship there. Magnetic field is mu naught. I'm not even going to write down 2 pi because that has no units, times current over length. So writing down all the units here. The magnetic field, we are measuring it in Tesla. That's the SI unit of magnetic field. So that should be given by, or this is actually equal now. That should be given by whatever unit of mu naught is. That's what we are trying to figure out, times unit of current, ampere, divided by length, meter. So to figure out the unit of permeability or magnetic constant, you just solve for this algebraically. Then you get permeability is equal to Tesla times meter per ampere. So Tesla times meter per ampere. And so this unit here could equivalently be expressed as Tesla times meter per ampere. And I think Wolfram alpha is comprehensive enough that when you look up permeability constant, that should be one of the units it gives the quantity in. I mean, this is, I guess, the most convenient one, but one of the units. Henry's, I don't like Henry's. All right, okay, so it's not in the list, but this is what I can do. Permeability first base in Tesla times meter per ampere. And it'll actually, Tesla meter, okay, there it is. I had to force it to give it to me, but it does when I ask it for that unit explicitly. When you give it wrong units, it actually wouldn't give you an answer. If I say Tesla meter squared per ampere, which is not a valid unit for permeability, it doesn't actually do that. It tells me, oh, these are the actual units. What are you talking about? So
Good. Any questions? So, so this is the simple numerical exercise, and what took longer is to describe all these unit relationships. And this is the last time I will explicitly mention units. Once again, with this advice that you always start out from the formula to figure out the unit. I don't even try to memorize these relationships. I'm just going to forget it. But if you start out from formulas, then you will always be able to get correct units. So I guess the burden that this places is that you have to remember the formulas correctly. In physics 4a, you could check if you memorize correct formula by doing dimensional analysis, right? In electricity and magnetism, I don't really do that because it's harder to memorize units than to memorize the formulas.